Um, if you're not happy with the lecture, I'm prepared to go over to the dunk tank. Okay, I'd like to talk with you about lead in water. There's not a lot of lead in water. Lead is present in water at extremely low concentrations, but lead is a very useful tracer or fingerprint of many different processes in the environment. And that's one reason why lead is so useful. Lead, of course, also a potentially toxic element and one that's very important to understand. So I want to talk about many aspects of lead in water, from the Arctic ice that I mentioned earlier to the faucet in your kitchen sink. Okay, so what I want to talk about first are peat bogs, and peat bogs as archives of lead in the atmosphere. And we've studied lead in the atmosphere going back in time 15,000 years. And then I want to talk about ice cores. And we've used ice as archives of lead in the atmosphere, also going back in time 15,000 years. And then finally, moving from the atmosphere to our soils. We've emitted lead to the atmosphere, okay, but what goes up must come down. And some of that lead in the soils is now slowly leaching into our streams and lakes. I want to mention that. And then, of course, I'll be talking about the beautiful groundwaters that we have in this area and the amazingly low lead concentrations. Bottled water, I have to say a few words about lead in bottled water. And then finally, tap water. There's been a lot of interest recently in the amount of lead in tap water and where it's coming from. So lead itself needs no introduction. Everybody knows what lead is. And you all realize that lead is used, for example, for making car batteries. But you also remember that lead had been used in gasoline. And this released a lot of lead to the atmosphere through the use of leaded gasoline. What you might not realize is that peat bogs are fantastic archives of changes in the atmosphere. So a peat bog is a kind of wetland, and it's an excellent archive of all kinds of things. It's an archive of human history. It's able to preserve things in the acid waters. This is the Tolland Man from about 3,000 years ago, perfectly preserved in an acid bog from Denmark. But bogs, as I said, are also archives of changes taking place in the atmosphere. And this is a summary of some work that we did in the past of lead in the peat bog going back in time approximately 15,000 years. So as we drill down through our peat bog, we're getting into older and older layers, and we're measuring the amount of lead that's in the peat. Because the amount of lead that's in the peat reflects the amount of lead that was delivered from the atmosphere. So just to summarize some of the highlights, the amount of lead contamination in the atmosphere until 3,000 years ago was zero. Okay, so until 3,000 years ago, there was no trace of lead contamination in the atmosphere. But starting 3,000 years ago, we have a 3,000-year history of atmospheric lead contamination. And we look at lead in the atmosphere a couple of different ways. One is looking at the amount of lead or the concentration of lead. But the other thing that we have in the case of lead is made up of different atoms, and we can use their ratio as a fingerprint. And if we look at the fingerprint and we describe it in the ratio 206 to 207 lead, we know that until 3,000 years ago, this fingerprint always had a value of 1.2. Okay? We don't need to understand all of the details of the fingerprinting method, but the point is our natural lead in the atmosphere had a ratio of 1.2. And that lead in the atmosphere, you're probably wondering, why was there lead in the air 10,000 years ago? But that lead is associated with soil dust particles. So simply dust in the air. But 3,000 years ago, and ever since, we have a completely different story. We have a completely different fingerprint, which is shown here in red, and we have significant contamination of lead in our atmosphere because of lead mining and because of coal burning and because of leaded gasoline use. So the point of this graphic is simply to explain that atmospheric lead pollution has a history of 3,000 years. So our atmosphere has been contaminated with lead continuously for 3,000 years. Ice is also an excellent archive of atmospheric lead. Okay, and these ice cores are so beautiful because they're in remote areas and they're giving us an indication of transport of contaminants from industrial areas to the Arctic. And they're perfectly preserved in this frozen ice. So my day job, I do have a day job. I'm at the University of Heidelberg in Germany, where I'm the director of the Institute of Environmental Geochemistry. And this is what Heidelberg looks like. And in Heidelberg, we've got some specialized equipment for measuring the amount of lead in water samples and in ice cores. And we have some experts like Michael who take care of this equipment. But we also have a special clean laboratory. Do you remember I said right at the very beginning there's not much lead in water, which is a good thing, but that means it's very difficult to measure reliably. So we need a special clean laboratory environment where we can work with our samples and not contaminate them. So our biggest challenge with lead in water is measuring it reliably because of our own contamination. We have a beautiful lab in Germany, but we don't have ice cores, and we started a collaboration with James Zheng and his colleagues at the Geological Survey of Canada in Ottawa, and he's at the glaciology group, and these are the experts on ice core drilling techniques, but also on decontaminating the ice core. If you collect an ice core, even using a titanium coring equipment, the first thing that's happened is the ice has become contaminated. So James takes care of all of the decontamination and then brings the samples to Germany for measurement. And this is a summary of lead in the atmosphere in the Arctic of the past 150 years. And you can see that the lead concentrations were increasing. So here's our concentration scale. It's been increasing. And then when we started using leaded gasoline, it increased dramatically, but it reached a point around 1970, and when we introduced unleaded gasoline, the lead concentrations in the atmosphere dropped off, which is good news. So lead concentrations in the atmosphere dropping off, and we see that clearly from the ice cores, but we also realize the natural amount of lead in the ice is even lower than that. Okay, the natural amount of lead in the ice is 5 parts per trillion, approximately. So we still have a ways to go, as we'll see in a coming graph. So James, a very industrious guy, very bright guy, he wanted to know what is the lead concentration like in the snow and ice today. So he dug a pit in the snow, 5 meters deep. He dug it by hand wearing his special clean room clothing to see the recent ice and snow layers. And this complicated graph shows us the past 10 years approximately. In the green, we see the natural amount of lead in the ice. In the red, we see that's the excess because of pollution. And you can see that there's very strong variation between winter and summer. So the air in the Arctic is very different between winter and summer. In the winter time, we have our highest lead concentrations when the air masses are coming from Eurasia. And in the summer, we have our lowest concentrations when the air masses are coming from Canada. But even today, in the Arctic today, in the snow today, the dominant inputs are still from human activities. And James has drilled an ice core going back in time 15,000 years, and these are his the latest results, and James has the first evidence of atmospheric lead pollution in the Canadian Arctic, and it started 3,000 years ago. So the measurements are so sensitive that we can see the beginnings of atmospheric lead pollution in Canada, in the Arctic, started 3,000 years ago. And we see pollution, again, this peak here, and the change in the fingerprint represents pollution 2,000 years ago from the Roman period. And there's pollution again 1,000 years ago. So what we see in the ice cores is we see that human activities have dominated lead in the atmosphere for 3,000 years. So there is a long history of lead contamination. And if we go back in time 15,000 years, the lowest lead concentrations in the entire ice core record are approximately 4,000 to 6,000 years ago. That's the cleanest ice layer. And in those ice layers, we have approximately 5 parts per trillion of lead in the ice. And I do want you to remember that number because I will come back to that. And this is a period of climate change that I won't discuss right now. But the natural amount, the lowest amount of lead in the Arctic ice, 5, 6, 7,000 years ago, and again, 5 parts per trillion. So what about our groundwaters in this area? Again, this area has a lot of artesian flows where water bubbles out of the ground, and I got real curious about the natural amount of lead in these waters. So here are some pictures showing these various artesian flows. Some of these things flow all of the time, and some of them have a small brass tap that you have to open to collect your water sample. Okay, and if we look at our lead concentrations relative to another element, okay, scandium has nothing to do with pollution. It's a little bit like aluminum, okay? It's just an indication of our mineral particles dissolved in the water. If we look at all of our samples, we notice that most of them show a natural ratio of lead to scandium. This is the ratio that we'd expect. The ratio should be about 2. But a couple of the water samples had too much lead, okay? And by too much, it's still a tiny concentration, but it's a little bit more than what we would have expected. Why is that? Because these sites have brass taps. So if we open the brass tap and we let the water run for an hour, even after an hour, we're still measuring a tiny trace of lead that comes from the brass. It has nothing to do with the water. It's simply from the brass tap because brass contains lead. That means when we look at all of our samples, these sites are discredited. We can't consider them, and we consider only the sites where the water is flowing all the time. Okay, and this is an example of one of these sites at the Bellows property. Okay, so we're very happy with our lead concentrations at these sites. Now, you remember I said that the cleanest layer of ancient Arctic ice had about 5 parts per trillion of lead. If we look at our groundwater, on average, 5 parts per trillion of lead. But some of our water samples below a part per trillion. These are among the lowest lead concentrations that have ever been measured in a natural water sample. So when we speak about lead, and we speak about these groundwaters, they're comparable, really, to the cleanest layers of ancient Arctic ice. And this is true not only of lead, but we've measured about 30 different elements, and several of those elements, many of them, are really comparable to the cleanest ice layers, which is fascinating. And as you know, the water is good to drink. Okay, what about our streams and our lakes? Well, as I said, we've emitted a lot of lead to the atmosphere over the past 3,000 years, and we wanted to know, is some of this lead now leaving our soils and entering our streams and lakes? So we went to a remote lake in Algonquin Park to collect some water samples. Here is our lake here. It's in a nature reserve where there's no camping, there's no trails. It was approximately 50 kilometers each way to reach the lake, and this is the team. It was a hard trip. We had to go over 17 beaver dams. Have no fear for the beaver population. They're doing well in Algonquin Park. 16 kilometers of portaging in a single day. I still feel it in my back. My back will never recover, I'm sure, but it was certainly worth it. And here is Cold Spring Lake, and this is collecting a water sample and trying to collect it without contaminating it. So we collected water samples at this remote lake, and it even rained one night. My colleagues were not so excited. I was over the moon. It allowed us to get a rainwater sample. Okay? And this is a summary of all of the data. I won't go into all of the details, but if the lead dissolved in the water is from the rocks, then the lead should have this fingerprint. But we can see all of our water samples have a completely different fingerprint, and that tells us the lead that's actually in the water is not natural lead from the rock, but it's slowly leaching out of the soils. So remember what I said, what goes up must come down. That lead that we emitted to the atmosphere, a small amount is now leaching into our streams and our lakes. Okay, so our lake water is mainly that industrial lead. The fascinating thing is we've also done some snow sampling, the rain sample. If we look at the rainwater, there's over 3,000 parts per trillion of lead in the rain. That's quite a high concentration of lead relative to some of these other water samples that we're talking about. And if we look at the amount of enrichment or the amount of contamination, our rain and our snow is strongly contaminated with lead. But if we look at our surface waters, our streams and our lakes, in fact, the extent of contamination is very, very low. So what does this tell us? The rain and the snow has quite a bit of lead in it, but that's not what we see in our lakes and our streams, because our forests and our soils are removing this. Okay, they're filtering it out. So these streams, rainwater comes in rich in lead, but somehow it's being removed by the particles in the soil. Okay, our streams might be rich in lead, but those particles tend to settle in the lakes, and our lake water is then poor in lead. So if we look at the lead in the lake, the concentrations are low, but most of that is not natural. It's leaching out from the soils. So the forest soils are excellent lead filters for a number of reasons. It was a very, very hard trip. It was a lot of work, but it was certainly worthwhile. Okay, what about bottled waters? Bottled waters, there's quite a story behind bottled waters. Bottled water is, as Pepsi Cola mentioned last week, it was in the news, it's often just tap water. So this is kind of a marketing genius. It's cola without any ingredients for the same price. The importance of this is such that we've brought in Tony Clark from the Polaris Institute to give us a presentation about bottled waters, and he's going to tell us what's inside the bottle. I just want to show you the leaching of antimony that I mentioned earlier. Here's our antimony concentrations, and again, this is parts per trillion. And here in black are different brands of bottled waters measured in November, and then the same bottles tested again 6 months later. So you can see the concentrations when they sit around for 6 months basically doubling. So we have antimony leaching out of the plastic into the water. And there's our natural amount of antimony in our local pristine groundwater. So you can see that with respect to antimony, that our water here is cleaner than any bottled water in PET plastic. Okay, what about lead? The purpose of my presentation here is to talk about lead. What about lead in bottled water? Well, there was a study published just a few years ago of bottled waters from across Canada. And they found that our bottled waters in Canada on average contain 5 parts per billion of lead. 5 parts per billion. A part per billion is 1,000 times more than a part per trillion. And when I looked at that, I thought, well, that sounds like quite a lot of lead. Maybe we should look at this a little bit more carefully. And here are our tests, 130 brands of bottled water, and in fact, the average is about 8 parts per trillion. So the previous value that I showed you that's been published is about 1,000 times too high. Okay, and the lead concentrations in the bottled waters in plastic bottles are similar to our lead concentrations in groundwaters. So when we look at these very low values in some of the bottled waters, that supports our data for our groundwaters for this area. Okay, so in fact, bottled waters in plastic, very low lead concentrations. And again, doing this work reliably can only be done under extreme clean lab conditions. Okay, so our values for lead in bottled water, about 1,000 times lower than previous data, and about 100 times lower than the data from Health Canada. What about glass bottles? When we published our study about antimony leaching from plastic, some people said, oh, I'm going to switch to glass. So we had a look at different brands of bottled water. Here's one brand, 6 bottles. Here's the data for lead in the plastic bottles in parts per trillion, but look at the values for the glass bottles. So if you have one brand of bottled water that you can buy in a PET plastic, or you can buy in glass, the brand in PET plastic is contaminated with antimony, and the brand in the glass is contaminated with lead leaching from the glass. Okay? And the way that we found this out is by testing these pristine spring waters that we have in this area. Okay, so here's bottled water from Fiji. I've seen it in London, Ontario. I've seen bottled water from Fiji in Ottawa. In London, Ontario, the tap water is about 1,600 times less expensive than bottled water. Okay, so this is a promotion from the City of Toronto promoting drinking of tap water. I grew up in Toronto. I've only drank tap water. I've never drank bottled water. What's happened recently, however, there's been some articles in the press about lead in tap water, and this started in London, Ontario. Okay, by testing some of the water in London, Ontario, some high values were found. Okay, so this is a kitchen sink in London, Ontario, and in this kitchen sink we have a tap. It's just a normal tap. The water is allowed to run, measure the lead concentration in the water, 400, almost 500 parts per trillion, or approximately half a part per billion. Okay, the drinking water standard, 10 parts per billion. So this water is significantly lower than the drinking water standard. But this tap here is deionized water. It's reverse osmosis water. So this tap here, if we measure the lead concentrations, we find virtually the same value. So how is it that the tap water and the reverse osmosis water have roughly the same lead concentration? Well, if we look at the fingerprint of the lead in this water and the fingerprint of the lead in this water, it's a completely different fingerprint. So the amount of lead is identical, but the source of lead is different. Okay, and if we have a look at this reverse osmosis water unit, which removes all the lead from the water, okay, it's followed by a brass tap. Okay, so somebody installed the reverse osmosis system to clean up all the water, connected it to the kitchens with a brass tap, and although the reverse osmosis system is removing the lead, the brass tap is adding it back again. Okay, so lead in drinking water, here are the questions that we're facing with, and they're difficult. What is actually being measured when we collect a water sample? And how should that sample be collected? And there's a number of possible sources of lead. The obvious one, lead pipes, but the lead pipes from the water mains are being removed in Toronto, they're being removed in London, Ontario, but lead also comes from brass, when brass contains between 1% and 5% lead. Steel pipes, steel also has lead added to it to make it easier to work with. Copper pipes will have lead solder, etc. And all of these things react differently. Okay, so this brings us back to the question, and I'll take 5 minutes just to go through this quickly. Why are the lead concentrations in our artesian flows here, why are these lead concentrations so low? And I can't say that we have the definitive answer, but we certainly have some idea. The ice sheets left this area approximately 13,000 years ago. Okay, so the ice sheets left, and they left behind all kinds of glacial material. So in this area, there are hills up to 100 meters high of boulders and rocks and sand and gravel that got dumped by the glaciers. So we're somewhere up in this area here. So the glaciers left behind a lot of material, but the Elmvale area, in fact, is sitting on some old lake sediments. Okay, so Lake Huron was much larger, and when the lake receded, it left behind a lot of sediments. So here we have our hills, which was deposited by the glacier as rocks and gravel and sand, and that's very permeable, okay? And the water can move through that very quickly. But down here in Elmvale, the so-called Elmvale clay plain, these are old lake sediments. So this is like apples and oranges. The coarse material, those big hills deposited by the glaciers, and when the lake evaporated, when the lake retreated, it left behind clay and silt. Okay, and underneath here, there must be channels of sand which can channel water. And these are permeable, there are water-bearing layers. Okay, so to give you a photograph of what this looks like, this is French's Hill. We're standing at the top of the hill. We're looking over the Elmvale clay plain. Georgian Bay is back here somewhere. We can actually see Collingwood, the ski hills over on the other side. So on the uplands, we have that coarse-grained boulders and sand and gravel deposited by the glaciers, and that's where our groundwater gets recharged. And then in the lowlands, these clay sediments, there's groundwater discharge. And that's where we have our artesian flows coming out of the ground. So here's roughly Waverly on the hills where we have a forest, coarse-grained material, and here are our artesian flows. Here is Georgian Bay. And I want to speak for a minute about this Parnell flow. This Parnell flow is very dear to my heart. I've sampled it many times over the past 3 years. It flows continuously. What is happening here is that water is evaporating, water is precipitating here as rain and snow on these hills, and then slowly making its way through these hills, then into our aquifer and flowing out over here. And that is our groundwater flow system. It's an oversimplification, but I think for the purposes of understanding lead, it's helpful. And again, there's channels of sand here which channel the water, and the water is under pressure, and that's why it's forced out of the ground. Okay, if we look at the Parnell flow, and as I said, I've tested it many times over the past 3 years, it has, on average, about 5 parts per trillion of lead, which is typical of all these other sites around here. So that's our value today. Now, sometimes when I speak with hydrogeology experts, they say, okay, well, that groundwater must be very old. That's why there's low lead concentrations. Okay, it doesn't have any lead contamination in it. So most people assume this groundwater is very old, and we wanted to find out how old it was. So we did some dating of the water. And the groundwater that bubbles out of the ground, it's not more than 20 years old. If it's not more than 20 years old, it's rainwater from the 1980s. And as Peter Dillon can tell us, and I'll ask him to quote me a number later, rainwater in Ontario in the 1980s had quite a lot of lead in it. If I had to guess, and it's only a guess, that rainwater from the 1980s, if rainwater today has still elevated concentration, certainly rainwater in the 1980s had thousands of parts per trillions of lead. So what has happened here? The lead is being filtered out of our system. Okay? This is like a natural water treatment plant. Even though engineers build water treatment plants and water treatment systems, okay, we understand all of that technology in the lab, on the pilot scale for entire cities, we still don't know how all of this works. But this is Mother Nature's natural water purification process. And at least 99.9% of the lead is being removed. So in the atmosphere, we've got rain and snow and dust particles, and in between we have soil, with all kinds of materials, organic matter and mineral materials. Here is our artesian flow, and this Parnell site is a very important reference site for us, okay? So we can see that this water is not only clean for drinking, it's also connected to our soils and it's connected to our atmosphere. And again, this is an opportunity to educate people about how our environment actually functions. Okay, to summarize, metals in waters can be so low in concentration, we need extreme procedures to be able to measure them reliably. And pristine groundwater, the lead concentrations really are at or below the levels of ancient Arctic ice. And our streams and our lakes, we now have lead slowly leaching in. And again, our soils are doing their best to filter that out. Bottled water, again, Tony Clark is here to talk to us this afternoon about bottled water. We have antimony leaching from PET plastic, and we have lead leaching from glass. And again, at this stage, I should just remind you, our EnviroClear bottles here that are reusable, dishwasher safe, refillable, those bottles there, of all of the bottled waters I studied from around the world, there was only one bottle that didn't leach antimony, and it's the EnviroClear bottles made of polypropylene. Okay, tap water, as I said, in the cities, they're removing lead pipes. Other sources of lead to the waters requires further study. And thank you very much for your attention.